And okay, today we are going to be talking about applications of trigonometry, which is the nice way of saying we're going to be doing story problems. The good thing about these is that they all kind of work the same way. And if you got how to solve those things with the triangles that you just got done doing, these are basically the exact same thing. You know, you're not going to be doing anything that's much different when we turn them into story problems. What I want to do first is we're going to show you 3 examples, and then you're going to go back and we're going to figure out exactly how to solve all of them and what you do on problems in general. So here's a beautiful picture of my artwork. And you can see this problem. It said Susie is 4 feet tall. She's standing 23 feet away from her beanpole brother. And yeah, he kind of is a beanpole brother in that picture. The angle of elevation from her eyes to the top of his head is 28 degrees. How tall is the brother? This is the classic trig story problem. You remember I said at the beginning of the chapter we were going to be going outside and figuring out things like how tall the lights on the football field are. Well, it's really no different if I'm figuring out how tall her brother is. I know something, I want to figure out how tall something else is, and that's exactly the idea. So then we have another beautiful piece of artwork, which I ended up making about a dog. Originally, I was going to write it about Nathan and Joe. And we were going to have Joe floating in the middle of the ocean, but that's but it does say a dog is at the top of a 1,000-foot cliff. The owner is flailing around in the ocean. The angle of depression is 56 degrees. And so we're supposed to figure out how far out that help is. That's what we're trying to do. And one more here, which I did actually write about one of my students I currently teach. We have Hollis is shooting pumpkins from a slingshot on the ground. He wants to hit his father in the head. Mr. Bodie is 6 feet tall and the pumpkin is 40 feet away from him. What should be the angle of elevation so that he hits the target there? Okay. So all 3 of those are pretty classic story problems that involve trigonometry. And they all actually involved a couple of terms that we need to make sure that you understand before we go on to solve them. And those terms are these 2 things: angle of elevation and angle of depression. Angle of elevation, most people kind of can figure out looking at the problem what it's got to mean. It tells you that it's an angle that you find by first looking straight across, and then you elevate your head. You turn your head upward. So you kind of pictured that pumpkin down on the ground, you go straight across the ground, and then you look up at Mr. Bodie's head. That's the idea of an angle of elevation. Angles of elevation are actually by far the most common thing that you encounter in story problems that involve trig, and they pretty much always are at the bottom of the triangle. That's where you're going to find them and look at them. The ones that people sometimes screw up are angles of depression. And technically, an angle of depression is exactly the opposite of an angle of elevation. You start by going straight across, and then you depress your head. You look downward, which actually means, and I'm going to go back until we get to that picture again. In the picture you're looking at here, well, the people that are quarantining won't see this as I get up and put my hand here. It is this angle at the very top is the one that we're talking about, the angle of depression. A lot of times people try and put it right next to the cliff instead of out in the air, but the angle of depression is going straight across and then you turn and look down. So it is that one that is at the very top. Now, when we actually do the problem, you're going to actually use the angle at the bottom down by the guy that's floating in the ocean. That's because you might remember from geometry that there's alternate interior angles in that picture. You don't need to remember the term, but you do need to remember that they're the same. So the angle at the top and the angle at the bottom are going to end up being equal. And when we get to solving the problem, that will actually be important. Again, angle of elevation, you look up, angle of depression, you look down. That's the big thing. So we're going to go through the steps we do to solve these, then we're going to solve a few problems, and that's pretty much where we're at here. So to solve problems like this, the first thing you want to do is label the picture. In a few minutes, you're going to actually get a little worksheet that mostly is problems that kids that were in this class like a decade ago made up. Later on, you'll get the chance to inflict problems on future generations. And you're going to find that the pictures sometimes are not drawn real well. That's why I kind of purposely drew mine badly, honestly. But you want to label the stuff you know and the stuff you're trying to find. Basically, what you're trying to do is take those problems and turn them into, let me go back, to what we just got done doing, where you've got a triangle and you find the part that's missing in the triangle. That's what we want to do. You write a little equation and you're going to solve it. I will tell you that probably literally 90% of the time, you're going to use tangent on story problems. All three of the problems I just did as examples will end up being tangent problems. There's actually a pretty good reason why tangent is most common. It's real easy to measure along the ground. That's fairly easy to do. The thing you're most often trying to find is a height, and those typically end up being adjacent and opposite to some angle that you know. That is very often what happens. If you had sine or cosine, the problem usually ends up being about like a ramp or a driveway or something else that's made of concrete or wood that goes diagonally upward, but you could measure right along it if you wanted to. The problem, if I was trying to like figure out how tall someone was, if I tried to do like the hypotenuse of a triangle, I'd be measuring through the air, and there's not a good way of doing that. So that is why most of the time it's going to end up being tangent for problems. Got one more step to throw in here, which is at the end of the problem, you do want to make sure you've actually answered whatever question's being asked. The very first problem we're going to do, that becomes important on, and I'll show you that in just a second. Sometimes what you get for X isn't actually what they want to know, and you need to do things like add or subtract something to make that happen. Okay? So we're going to do those three problems, and you're going to find out none of them is really very hard to do. We're going to go back to Susie and her beautiful brother. And again, it tells you she's 4 feet tall. She's standing 23 feet away from her brother, and the angle of elevation is 28 degrees. So for just a second, I'm going to go back to the blank picture. It told you in the problem she was standing 23 feet away from her brother. Where would I label that if I was labeling this picture? Garrett? The line across from the head. Now, when I asked that question first period, they told me on the ground. They're both right, because the line on the ground from her feet to his feet is going to be the same as from her head to his waist. It is going to end up being the same answer, and that's 23. The angle of elevation would be by her head. It's the bottom of the triangle, basically. The other piece of information I know is that she's 4 feet tall, and if I was labeling this, I'd probably put a 4 over by her. Does that kind of make sense looking at the way I've got this picture labeled on here? So I already told you this is a tangent problem. Now, I will tell you, I have X labeled as the entire guy's height here, which is what we're trying to find. But what we're really going to find is the side of the triangle, like from his head down to his waist. And that's like the opposite side of the triangle when I start setting it up. What's going to happen when we get to the end of this is we're actually going to have to add 4, because we get from her head to the top, but we still need to add the part that's missing there, which is the 4 feet tall she is. Well, I told you this was a tangent problem. And if you think about how things are set up here, opposite would be like x, adjacent is 23, that's like the bottom of the triangle. And so tangent of 28 must be x over 23. You can see I multiplied to do this, and I ended up getting like 12.2. We will have to add 4 to actually figure out our answer. And this problem is very similar to a lot of things you'll see on worksheets in that we get a really stupid answer. Her brother is 16 feet tall, 16.2 feet tall. And since you're going to see problems that students made up in the past and that I made up just by basically making random numbers, you will get stupid answers. That's okay. You know, don't worry about it if somebody does end up being 16 feet tall. That happens all the time in these story problems. You do want to actually think, so does that answer make sense compared to what we have? And looking at the fact that it's across from a 28-degree angle, yeah, 12 makes kind of some sense as part of that triangle, because I know it's got to be shorter than the bottom length. Okay. So, yeah, it's not an answer that's impossible. It's just like a stupid answer in terms of the height of an actual person. Everybody see what we did with that one? Okay, so then we'll get to this problem. 1,000-foot cliff. Well, I'd label the cliff to be 1,000 feet. And I will tell you, when we do that, we're actually assuming the dog is like 0 feet tall. Because really it's like probably going to be like 1,002 or something, but it's not going to make enough difference to matter in terms of the overall problem. Again, it tells us an angle of depression. And the idea of an angle of depression, again, is technically it's going to be at the very top of the picture. But what we're going to use to solve the problem is at the bottom of the triangle right next to where it says help. Okay? Which is why when I write my equation, this one's going to say the tangent of the 56 that would be at the bottom equals 1,000 over x. Do you guys see where I'm getting that looking at the picture? Does it also make sense why I divided to come up with my answer on this? Because x is on the bottom of that. When people do this wrong, they'll actually like label the 56 next to where I put it in the picture there at the top, and they want to do it upside down and they get a wrong answer because of that. But, again, if you kind of always use the bottom of the triangle, you'll pretty much always be right. We do end up with 674, and all I want to know is how far out at C is, so I don't need to add or subtract anything. We're good to go. That's it. Any question with that one? So finally, the last example here with Hollis and his dad. And we have this slingshot on the ground. He's shooting a pumpkin. His dad is 6 feet tall, and he's 40 feet away. So first off, where do I put the 6? Yeah. Next to the person, yeah, which is presumably Mr. Bodie, who's lost weight. And the 40, I'm pretty sure, is on the ground. What's x in this problem? And there's the question. It is going to be the angle, and there's only one angle inside the triangle that we could possibly find, which is where the pumpkin is. You guys all see where that's coming from. Can anyone tell me an equation for this problem? So, yeah, it is going to be tangent x equals 6 over 40 is exactly what you end up with. And this time we're trying to find an angle, which is why you would do like second tangent to come up with your answer, inverse tangent of 6/40ths. And it ends up being like 8.5 degrees. About 9 degrees is what you'd have. Now again, the picture is not drawn accurately. That's because compared to how tall a pumpkin is, probably Mr. Bodie is going to end up being a little bit further away for 40 feet than the 6 feet tall that he is. And it would be really a much wider and less tall triangle if you drew it realistically. But, it's going to end up being the smallest angle of the triangle. And so, yeah, 8 to 9 degrees does seem like a reasonable answer for what you'd come up with on that. You guys see how we're setting these things up? Then today you're going to do a few of those problems, and probably tomorrow we're actually going to end up going outside and figuring out how we'll do that. And after that, later in the week, you'll actually start doing the project of working with things outside.